So we left off here at chapter 17, so this is part 2. There can be an effect of multiple substituents. So for example, if we have this para-nitrotoluene, both the donating group of the alkyl and the withdrawing group over here will direct the nitration on the ortho and meta to nitro group. So this allows the reinforcement of both these groups at this position over here. So if we have metaxylene with two methyl groups that are donating, it'll be ortho and para directing. So in this case, this ortho is hindered, whereas these are ortho and para to one another and accessible. As a result, this one doesn't form, generating the major product shown here. So in this case, you have an ortho and a meta director. This is your ortho para, and then this is your meta director. And because the meta director is non-dominant, you're going to have this one dominating with ortho and para being preferred. But this site is activated but crowded. As a result, you're going to have these two products in the sulfation. So let's do a problem of bromination of this molecule shown here. Here's the animate group. This is a strong activating group, whereas your chlorine is not as strong. As a result, you're going to have ortho, right, and para, but this is in the para position already taken up. So you're going to have orthobromination, so your product here as well as the other product over here, dibromination product, because of the fact that this is a strong activating group. A reaction in terms of alkylation is called Friedel-Crafts alkylation, in which you have your benzene in the presence of an alkyl halide shown here and Lewis acid. We've seen aluminum trichloride, iron tribromide. This will substitute this H with an R, alkylating the benzene. So if we look at the mechanism of Friedel-Crafts reaction, you have your tert-butyl chloride. This is your alkyl halide, in which the electrons from your chlorine go to the aluminum trichloride, forming carbocation. The carbocation then reacts with the benzene. Electrons in the ring come out. This generates 3 possible resonance structures shown here, in which your electrons can move. Generating these sigma complexes, and then the remaining AlCl 4 minus will then come in, chlorine, and pluck off the hydrogen, quench the positive charge, and regenerate the catalyst and the product. You can also take alkenes in the presence of hydrofluoric acid. This will protonate, right? Forming the cation shown here. The cation then reacts. Again, this is a shorthand version of the 3 possible resonance structures, right? But when in an exam, I'd like you to draw these out. Then the fluorine that's from here will pluck off the positive charge, generating the the resonating conjugated structure. So here, this weak acid is preferred HF, because fluorine ion is weak nucleophile and won't attack the carbocation. Alcohols and Lewis acid. So if we have an alcohol in the presence of a Lewis acid BF3, electrons will conjugate with the BF3 to form the complex, which will then make it a good leaving group and then leave, forming the carbocation. So there are limitations of the Friedel-Crafts reaction. It fails if benzene has a substituent that is more deactivating than halogens. Rearrangements are possible, and alkyl benzene product is more reactive than benzene, so polyalkylation occurs. So let's look at the case or the scenario of rearrangements. If we have isopropyl chloride in the presence of aluminum trichloride, you form, right, the complex. Complex then wants to react where the chlorine wants to leave, but in addition to the chlorine leaving, the proton moves over, or the hydride moves over, generating your carbocation over here, the more stable carbocation. This will then react with the benzene to generate isopropyl benzene. Let's do another problem. Devise a synthesis for paranitro tert butylbenzene from benzene, and so you can start. There are two possible reactions. One is to do Friedel-Crafts alkylation, adding the tertiary butyl group. This is donating, and then it'll favor ortho and para, and so in the presence of the nitration reagents, it'll nitrate on the para position plus the ortho group, so you should show both. Now, if you can do it the other way, in which you nitrate first, nitration will then is a deactivating group, right? It's electron withdrawing, and so it'll prefer the alkylation at the meta position, so as a result you don't get the para. So this would be a bad synthesis. In addition to Friedel-Crafts alkylation, you can undergo Friedel-Crafts acylation, in which you use an acyl halide, right, in the presence of your catalyst, and you can add that acyl group right onto the benzene. Here's acetyl chloride, AlCl3, acetylbenzene. So in the mechanism of acylation, the first, again, step is where the chlorine attacks, forming a complex in which now the chlorine is cleaved, generating your acylium ion, which can undergo resonance. So if it undergoes resonance, what's happening here is you can have electrons from your oxygen come in, forming a triple bond. Then you have electrophilic attack from your benzene, and then again, this is a shorthand version of the resonance structures, but you're going to want to show it out in your exams. Once you generate this, you're going to deprotonate, so then the aluminum tetrachloride will come in, attack, will leave, form the acyl benzene. Some important thing to note is that Friedel-Crafts acylations are generally free from rearrangements and multiple substitutions, so they do not go on strongly deactivating rings, however. Another reaction is the Clemmensen reduction. So once you first acylate your benzene in the presence of a catalyst, you generated the acylated product, and then in the presence of zinc, mercury amalgam in aqueous hydrochloric acid, you can actually reduce that so that it's an alkane. So Clemmensen reduction is a way to convert acyl benzenes to alkyl benzenes by essentially treatment with this reagent. Nucleophilic aromatic substitution. So here's your starting molecule to 4-dinitrochlorobenzene. In the presence of ammonia and heat and pressure, you can actually substitute this chlorine with the amine, generating the substituted product. So a nucleophile essentially replaces the leaving group on an aromatic ring. In this case, it's the chloride. This addition elimination reaction, and the electron withdrawing substituents activate the ring for nucleophilic substitutions. These are electron withdrawing. So the mechanism of nucleophilic aromatic substitution is as such, where your first is your attack of the hydroxide onto this position, kicking out the electrons over here. Now you have resonance structures shown here in which your electrons from that you just kicked off can go into that C-N bond, and electrons go to the oxygen, generating a product over here. The other way it can go is if these electrons go and move over here, now go to this position. Again, the electrons from here can go into the nitrogen, CN, kicking out the electrons over here to the oxygen, generating this product. And the other possibility is if the electrons here go inside and go to this corner, which generates this product. Step 2 is the loss of chlorite from this ring, in which now you have your electrons coming in, kicking this out, generating phenol. Phenol, in the presence of this OH minus, the base, will deprotonate, right? We'll pluck off that proton. Generating phenoxide. So in terms of the activated positions, in the case of nitro, you have ortho and para. These are the activated products, right? But the meta is not activated. So nitro groups ortho and para to the halogen stabilize the intermediate, and the transition state leading to it. Electron withdrawing groups are essential for the reaction to occur. In terms of the benzyne reaction, elimination addition, here's para-bromotoluene in the presence of sodium amide and ammonia. You generate substitution. Para, as well as, interestingly enough, the meta substitution. Reactant here is halobenzene with no electron withdrawing groups on the ring. So you use a very strong base like NaNH2. If we look at the mechanism, NH2 will deprotonate, generating electrons over here, and then your electrons will come down, kick off the bromine, in which you have two pi systems, which will form this triple bond. So sodium amide abstracts proton, benzyne intermediate forms when the bromide is expelled, and electrons on sp2 orbital adjacent to it overlap with the empty sp2 orbital of the carbon that's lost. It's bromide. And these benzynes are reactive species due to this high strain that's shown here in the triple bond. So once you have your benzyne, then your amine comes in, attacks, kicks the electrons over here. This will then pluck off a hydrogen from ammonia, generating the para. You can have then the NH2 come in on the metacarbon. Electrons are pushed over here to this para. This will pluck off a hydrogen, generating this meta 50%. So important thing to note is that with strong electron withdrawing groups, ortho or para, the addition elimination mechanism is more likely. Without these activating groups, stronger conditions are required and the benzyne mechanism is likely. Aromatic substitutions using organometallic reagents. Friedel-Crafts reactions have limitations. They have rearrangements, multiple alkylations, cannot occur on deactivated rings, and you need strong electrophiles. Organometallic reagents can add alkyl groups to benzene without these limitations. So, here's organocuprate reagents in which you have alkyl halides in the presence of lithium forms alkyl lithiums. You can take 2 alkyl lithiums in the presence of copper to generate this dialkylated copper or cuprate reagent. These are called Gelman reagent. So you can use these organocuprates and couple. Here's iodobenzene. This is lithium divinyl cuprate, and it'll generate styrene. Here's another alkyl halide in the presence of the aryl cuprate, and will generate the product shown here. So mechanisms vary depending on the alkyl halide, and the organocuprate used cannot be SN2'd because vinyl and aryl halides work well. So let's look at the Heck reaction. The Heck reaction, you can take an aryl or vinyl halide where it's a Br or I reacted with a double bond alkyl group in the presence of palladium, catalyst, and base will generate the product shown here. So it'll couple aryl or vinyl halides with an alkene, produces a carbon-carbon bond at the less substituted end. So right, it's taking the less substituted end over here instead of this side. Triethylamine or sodium acetate is added to neutralize the HX produced. So examples of the Heck reaction are shown here. Iodobenzene, styrene in the presence of your catalyst will generate this transtylbene. You can have an aryl halide with this methyl acrylate. Again, it'll on the least substituted side, generating the methylcinnamate. Iodobutene, acrylonitrile, generating this conjugated nitrile. The Suzuki reaction can take an aryl or vinyl halide. In this case, it's Bri or chlorine. The presence of a boronic acid, palladium catalyst, and base will generate the coupling of the RR, right? Boronic acid as your byproducts in sodium halide. This is called Suzuki coupling. Palladium catalyzed substitution that couples aryl or vinyl halides with alkenyl or aryl boronic acids or boronic esters. So if we look at the synthesis of boronate esters, here's your alkene, the presence of a dialkoxyborane. You're going to get addition of the H and the Br, just as we had shown previously with hydroboration. I'm going to draw the alkene right below so that you can see it, so please bear with me. So your hydrogen, right, comes down, and your form the product shown here. Same thing again, where I'm not going to show you the mechanism for here, but you can do the same thing and draw the alkyne right underneath, and your halogen on the more substituted side, the boron on the least substituted side, so you generate these. The boronate esters can be synthesized from alkyl, vinyl, and aryl boronic acids, can also be made by the hydroboration of double bonds and triple bonds. So the examples of the Suzuki reaction are shown here. Here's a vinyl halide in the presence of an alkenyl boronate ester. Palladium will generate here with both E and Z stereochemistry. Here's periodophenol, phenyl boronic acid, in presence of your catalyst, generate this paraphenolphenol. Palladium and carbon reactions with this is here will attach at the boron to generate the product shown here. Chlorination of benzene, if we take 3 equivalents of chlorine and then heat and pressure or light, you generate benzene hexachloride. So this is allowing you to add chlorine under these conditions. First Cl addition is difficult, but the next 2 moles add rapidly. You can do catalytic hydrogenation, so in the presence of 3 equivalents of hydrogen, very high pressures, but in the presence of catalysts, the number of them shown here, you can reduce, right? And rather than reducing just a single bond, it reduces the entire thing to the cyclohexane. Birch reduction, in the presence of sodium or lithium, ammonia, and alcohol, this will take the aromatic ring and generate the 1,4-cyclohexadiene in about 90%. Mechanism for birch reduction, first step is your ammonium and the sodium will generate ammonia with electrons, an ammonia cation. Electron again goes in here, and then electrons are pushed down to generate this radical anion, which we've seen before, right, in the reduction of triple bonds into double bonds. Then these electrons here will pluck off the proton from the alcohol, generating just the radical, and then the electron will come in, making the electron pair, which will then protonate off of the alcohol, generating the cyclohexo-1,4-diene. So the limitations of the birch reduction. We have a carbon bearing an electron withdrawing group carbonyl. That position over here is then the position that gets reduced in the birch reduction. However, if you have a carbon bearing an electron releasing alkoxyl group, that position is actually not reduced, rather the position over here is reduced, as shown here. You can have side chain oxidation. Here's a molecule in which you have the methyl substitution shown here, and also another alkyl substitution here in the presence of potassium manganate in base, water, heat. These two get oxidized, and then in the presence of acid, protonated to generate the acid. We have even an alkene and an acyl chain. These two will get oxidized all the way up to the acid. You can also use sodium dichromate and sulfuric acid in heat. Again, that would also bring it all the way up to the acid here. So alkyl benzenes are oxidized to benzoic acid by heating in basic KMnO4 or heating in the chromate solution, and the benzoic carbon will be oxidized to the carboxylic acid. Side chain halogenation, so here's ethyl benzene in the presence of Br2 or NBS in the presence of light. At the alpha position will become brominated, and then you'll have trace methods of the alpha-alpha dibromobenzene. This is just to show that the benzoic position is the most reactive. Br2 reacts only at the benzoyl position, or benzoic position. Cl2 not as selective as bromination, so you have mixtures. In terms of the mechanism for side chain halogenation, it is shown here. It's radical, so it'll pluck off hydrogen by forming a bond, and then radical forms over here. Now you have resonance, where you can have electrons move that radical around, shown here, and then the radical can then be quenched, right? So these two form chloride bound, regenerating a chlorine radical. And in the presence of chlorine and light, this will happen again to generate the dichlorine molecule. Important thing to note is that in predicting reactions on side chains of aromatic rings, consider resonance forms that delocalize a charge or radical electron onto SN1 reactions. So benzylic carbocations are resonance stabilized, easily formed. Benzyl halides undergo SN1 reactions. So in presence of ethanol and heat, will leave to form the carbocation. And then the rest of the mechanism where you have electrons from your oxygen come in, form the adduct. Sorry for my atrocious handwriting here. You're going to have to deal with it. And then this will get deprotonated by ROH and get the product. SN2 reactions, benzylic halides are 100 times more reactive than primary halides via SN2. The transition state is stabilized by a ring right here, right? So this is your transition state. It's being stabilized by that overlap while the nucleophile is coming in. Examples of SN2 reactions of benzyl halides. So you can brominate, right, to generate the benzyl halide. And then you can have SN2 reactions in which your electrons, this is your alkoxy group, and then bromine gets kicked off again. You can have cyano group on the, and then kicking off electrons from the bromine. Oxidation of phenols to quinones. Here's metacresol. The presence of sodium dichromate, sulfuric acid. You get oxidation to this quinone. So phenols react with oxidizing agents to produce quinones. Quinones are conjugated 1,4-diketones. This can also happen slowly in the presence of air. You can have electrophilic aromatic substitutions of phenols in the presence of HF, right? You're going to have both para and ortho. Phenols are highly reactive because the hydroxyl group stabilizes a sigma complex form, usually alkylated or acylating using relatively weak Friedel-Crafts catalysts such as HF. So you want this one to avoid over-alkylation or over-acylation. And so this ends Chapter 17.